Hello everyone, this is Gnaneshwar Sairam Indrala from CSE Department A section, roll number 21951A0552, and this is my chemistry PPT, subject code AHSC06, and my topic is an effective method of estimating state of charge of lithium ion batteries based on the electrochemical model and the Nernst equation. Introduction. With the numerous advantages such as high energy density, low self discharging rate, no memory effects, and long lifespan, and so on, lithium ion batteries are generally regarded as a leading energy storage candidate for an electric vehicles, renewable energy systems, portable electronic devices, and the many other applications. In most lithium ion batteries, energy storage systems, a battery management system BMS is employed to manage the performance and maintain a longevity of the battery cells. The functions of a BMS include mainly cell voltage detection and balancing, estimation of cell state of charge and state of health, and terminal management defined as a ratio of the reducible charge stored in a battery to its maximum availability capacity. The SOC is one of the primary and the crucial parameters critical parameters of the development of the battery management strategies. Accurate SOC estimation plays a vital role in controlling a safe charging and the discharging of the battery life guaranteeing in effect efficiency. However, the SOC cannot be measured directly and accurately by sensors like ordinary physically content in practices. Despite a huge research efforts, the battery SOC estimation still poses a significant challenge due to the complexity and the non-linearity of electrochemical reactions. A. Review of SOC estimation method. According to whether SOC estimations used for online applications or the SOC estimation method can be divided into offline and online estimation methods. Offline estimation methods may mainly include the open circuit voltages OCV, electromotive force interresistance and impedance spectroscopy through generally simply and rapidly implementable. They have greatly strict requirements for experimental conditions and time because these methods need to interrupt normal operations of the battery. They are only suitable for measurement in laboratories or as cross checked for other estimation methods. The online estimation methods mainly include the Coulomb counting, computer intelligence methods, and the model based methods. The CC method computes the SOC by integrating the battery loading current over time and requires an accurate initial SOC. However, finding the accurate initial SOC itself is a challenge. Also, its estimates as susceptible to current drift and measurement noise. The computer intelligence based methods eliminate the battery SOC by utilizing some of intelligent algorithms such as genetic algorithm, practically swarm optimization, physiologic neural network, and support the vector mission, etc. Treating the battery as a black box system, these methods approximate the relationship between the SOC and other variables by training the approximate model with a large quantity of experimental data. promising accuracy can be achieved with reliable training data, but these methods may fail in unexpected training conditions. The model based SOC estimation methods have attracted considerable and attentions due to its remarkable advantage of closed loop control and insensitivity to unexpected disturbances. This reported model based on SOC estimation methods mainly differ from the battery models and observes employed in the methods. Commonly used battery models include equivalent current models ECMS and electrochemical models EMS. In ECMs, the characteristics of the circuit elements such as voltage source, resistance, and capacitance are applied to stimulate the battery dynamics. Simple and flexible model structure of ECMs promote their control- controllability and applicability in practices. However, the ECMs fail to give the full expression of the battery dynamics due to the lack of representations of physiochemical reactions inside the battery. Different from ECMs, EMs derived based on the electrochemical reactions mechanisms, thus the capacity of the elaborate the battery dynamics such as lithium ion diffusion and inner calculation, de-inner calculation. Knowledge of these dynamics inside the battery significantly enables more reliable and accurate battery state elimination. The development of EMS with the control algorithms, however, is severely hampered by their complexity. The most frequent used observations in this model based SOC elimination methods include H infinity filter, Derivative Kalmson filter, particle filter, and the sliding mode observer. While the use of these observers can be improve the accuracy of the models and the SOC elimination, they bring extra complexity and computational efforts to the estimation algorithms. It is it is also worth mentioning that most of the observed parameters are usually determined by the exponential knowledge and need to be calibrated by a tedious procedure. This is not associated with the mechanisms of electrochemical reaction inside the battery. Very few reports investigated observers from the perspective of the electrochemical mechanisms to improve the performance of the model based on the methods. More efforts are therefore need to be address these issues. B. Key constraints. To address the knowledge gaps mentioned above, a novel EM based battery SOC elimination method is proposed in this paper, and the key contributions of the work are summarized as following. Number 1. An approach of the perspective of electrochemical mechanisms is proposed for the eliminating lithium ion batteries SOC based on the battery single practice model and the next equation. Number 2. A simple voltage negative feedback is applied to the eliminate the voltage error between the battery reference terminal voltage and the model output voltage. The relationship between the voltage error and the current among of lithium ion constraints is solid phase quantitatively deduced by using the Nernst equation. Number 3. Robustness of the effectiveness of the proposed SOC elimination method are systematically validated using different Operating situations include various charge, discharge, current rates, cell aging, levels, erroneous, initial SOCs, or dynamical conditions. C. Paper organization. The remainder of the paper organizes as follows. Section 2. Introduce a battery, simplified battery EM, to depict the electrochemical reactions inside the battery. The proposed battery SOC elimination method based on the lithium ion constants. The next equation is present, presented in section 3. In section 4, demonstrate the experimental results and the discuss, followed by the summary of the main conclusions and the future work in section 5. Section 2. Battery eliminated electrochemical model. As shown in figure 1, a systematic of typically battery EM1D Pactal model consists of a proposed of negative electrode, a phosphorus positive electrode, an electron blocking separator, and electrolyte. When the lithium ion battery is charging, lithium ions deintercalated from the positive electrode and passes through the separator to the negative electrode. The more lithium ions incalculated to the negative electrode, the more energy is charged into the battery. On the, on the contrary, during the battery discharging process, lithium ion intercalculated from the negative electrode and then travel across the separator to the positive electrode. Systematic of a lithium ion battery electrochemical model. And the yellow circles are solid particles in negative electrode, and the blue circle says lithium ion, and the red colored circle says solid particles in positive electrode. And the leftmost is a negative electrode and the rightmost is a positive electrode. In the middle there is a separator, that is electrolyte. Going to the next slide. In the model, the lactic structure of the lithium ion battery electrode is visualized as small spherical solid particles. They are assumed to uniformly disperse along the x-axis to hold lithium ions in the solid phase. The intercalation process of lithium ions are visualized by the ions moving in and out of the spherical solid particles. During the charging and the discharging, the lithium ion and the charges in the positive and the negative electrodes and the liquid are conserved. Table 1 lists the governing equations of describing the dynamics of the lithium ion batteries. More details are about the dynamics of the lithium ion batteries can be found in the literature as listed in table 1. The dynamics of the lithium ion batteries can be described by the set of partial differential equations PDEs. These equations are difficult to apply direct in practice, especially for the development of advanced EM based algorithms. And these are the equations. And on the right side, this is a description of the every equation. You can take a screenshot for further use. This is the table 1, the dynamic behavior of lithium ion batteries. Let's move on to the systematic of SMPs of lithium ion batteries. In the leftmost yellow circle is the negative electrode and the rightmost is the positive electrode. In the middle there is a separator and the right is and the right image is not meshing of radius. Clear? To simplify the model, each electrodes of the battery can be visualized as a single spherical solid particle that hold the lithium ions in each of its layers as shown in the figure 2. The simplified model is known as the single practical, practical model SMPs. This approximation also studies in literature. In SPM, the lithium ion concentration in the electrolyte is dimmed to be uniform, and namely dCe by delta T is equals to delta C by delta X is equals to 0. Thus, the SMP consider mainly the solid phase lithium diffusion, the total number of lithium ions, and the minimum lithium constraints in the solid electrode can be determined by the following equation, where NS total and CS mean denote the total number of lithium ions and the main lithium ion constraints in the solid electrode respectively. Equation 8 and equation 9 can be further described as the following equations 10 and 11. The mean lithium ion concentration by the electrode can be employed to compute the battery associated by equation 1 as follows. The output voltage, U, of the SMP can be determined by the following equation, where delta 0 plus, T and delta S of 0 minus, T denotes the potentials of the positive and the negative electrode respectively, and the Re represents the imperial contract resistance of the battery. The electrode potential delta of the battery can be calculated by the following equation. By submitting 14 into 13, the output voltage can be rewritten as Ut is equal to delta T minus It of Rc. By combining 1, 7, the output voltage can be obtained as the following, where Cs of Rp, T and Cs max denote the outermost lithium ion concentration and the maximum lithium ion concentration respectively. R sum is the sum of contact and the SEI film resistances, and UCS RTT represents the open circuit potential of the electrode. Third, number 3, the proposed SOC elimination method. Feedback voltage error and lithium ion concentration correction. As shown in figure 12 and 16, the SOC and the model output voltages are strongly related to the lithium ion concentrations of the solid phases. During the battery charging and the discharging process, the cell terminal can be accurately measured by the voltage sensors. A simple voltage negative feedback is employed to observe the voltage error between the referenced cell, the terminal voltage and the model output voltage. It is necessary to eliminate the voltage error by correcting the lithium ion concentrations to ensure the model can be precisely mimic dynamics from the lithium ion batteries, thus achieving an accurate SOC elimination. Assume that at a time of instant t equals k, there are errors between the estimated and actual values of the SOC and U, noted as 1 SOC and 1 U respectively. For the purpose of eliminating the errors, and the amount of correction of the lithium ion concentration is added at the end of instant t is equals to k plus 1, and the revised lithium ion concentration values can be calculated as the following, where I is equal to 2, 3 2 up to n1, comma k is equals to 2 comma 3 up to n2, delta cs plus k plus 1 and delta cs minus k plus 1 denote the corrected amount of lithium ion concentration of the positive electrode and the negative electrode at the time of t is equals to k plus 1 respectively, and represent the revised lithium ion concentration in the positive electrode and the negative electrode at the instant k plus 1 respectively. By submitting 17 into 11, the current the corrected mean lithium ion concentration can be calculated by the equation below, where cs where delta cs mean k plus 1 and delta cs mean k plus 1 denote the revised mean lithium ion concentration in the positive and the negative electrode at this time instant k plus 1 respectively, and denote the corrected amount of mean lithium ion concentration in the positive and the negative electrodes at the time instant k plus 1 respectively. Based on 12 equation number 12, the battery SOC can be calculated by using the lithium ion concentrations of the positive and the negative electrodes respectively as following equations. The SOCs calculated by 19 and 20 should be equal, namely SOC plus is equal to SOC minus. By submitting 22 and 23 into 24, the relationship between the main lithium ion concentration of positive and the negative electrodes can be obtained as the following equations. In relation between the mean lithium ion concentrations of positive and negative electrodes before and after concentration can be obtained from 25 as following. By submitting 8 and 20 into 26, the relationship between these two can be obtained as delta cs k plus 1 is equals to k of delta cs mean k plus 1. By submitting equation 19 and 21 into 27 can be obtained by the relationship between delta cs k plus 1 and delta cs k plus 1 as delta cs k plus 1 is equals to delta cs k plus 1. B. Next equation for the correction lithium ion concentrations. Although the relation between the model output voltage and the lithium ion concentrations can be expressed in equation number 16, it is difficult to directly reduce the corrected amount of lithium ion concentration according to the voltage error, and to address the issue, the next equation is employed in the work of computing and the correcting the lithium ion concentrations. The next equation describes the quantitative relationship between the standard electrode potential activity of reactants and reversible potential cell electrode in the concentrate and reversible potential of the cell electrode. It is concentrate manufacturable of thermodynamic equilibrium in the process of electrochemical reaction for the cell reaction as shown as AA plus BB is equal to CC plus DD. It's a reversible reaction. Electropotential can be calculated by the next equation as follows, where delta 0 denotes the standard electropotential, n represents the number of electrons transferred during the reaction, and A represents the activity of the counterpart electrochemical reaction in the positive and the negative electrode of LiMn 204 batteries during the reaction, where positive and negative denote the substances in the positive and negative electrodes respectively. The degree of embedding in usually used to replace the activity, which refers the ratio of the embedded quantity of the maximum embedded quality in the current state. In the paper, embedded quality of the lithium ion is expressed by the mean ion concentrations, and therefore the relationship between the activity and concentration of lithium ion are as shown. The scheme of proposal SOC elimination method is shown in figure 3, the initial value of battery model volume 8. You can take a screenshot and read it later. Conclusion. In this paper, a approach of based on a battery EMI, the next equation was proposing for the estimating the SOC of lithium ion batteries, a single particle model that reduces the complexity of the typical battery EM while maintaining the capability to capture the battery dynamics was employed in the work to provide a direct insight of the compute the lithium ion constants in the solid particles. The voltage and the voltages can be used to correct the lithium ion concentrations through a simple voltage negative feedback module. The corrected amount of the lithium ion concentration was quantitatively reduced. By the next equation, the performance of the proposed method has been validated under different operations conditions including various charging and discharging current rates. NORS institution initial SOCs and selling values experimental results shown that although an erroneous initial SOC of 50% was applied to the proposed algorithm, promising estimates that the mean absolute errors less than 1.35% could be still achieved for both constant and dynamic loading conditions, demonstrating the high degree roughness and the effectiveness of the proposed SOC elimination method.